All right, I'm going to walk through the page 238 assignment with you and explain everything. So here's number one, and it's matching. And one thing I notice is that the easiest ones probably would be part C. Notice that it's concave down the whole time. If the function is concave down, then the second derivative is negative. And part B, same idea. Notice that it's concave up the whole time. If the graph of the function is concave up, then the second derivative is positive. And then notice that A goes from being concave up to concave down. That means the second derivative goes from being positive to being negative. And here we notice it goes from being concave down to concave up. That means the second derivative goes from being negative to being positive. Okay, so based on that, we should be able to match things. Part A, the second derivative is negative. That would be C. Part B, the second derivative goes from positive to negative. That would be A. Part C, the second derivative is positive. That would be B. And part D, the second derivative goes from negative to positive. That would be D. Okay, number 5, determine the intervals on which the function is concave up or down and find the points of inflection. So we're going to take the first derivative. That would be 30x squared minus 5x to the fourth. And then the second derivative, that would be 60x minus 20x cubed. We want to see where the second derivative equals 0 or does not exist to get the potential inflection points. This is always going to exist. There's not going to be any does not exist points because it's just a polynomial. So we have 60x minus 20x cubed equals 0. Let's factor 20x out of both terms, and we have 3 minus x squared as the other factor. Set each factor equal to 0. And we get x equals 0. We get x squared equals 3, so that one would give us x equals plus or minus square root 3. So here are the potential inflection points. We don't know that they're inflection points until we find the intervals and test them, but these are the numbers we're going to use to break the number line down into intervals. So we have the interval from negative infinity to negative square root 3, the interval from negative square root 3 to 0, the interval from 0 to square root 3, and the interval from square root 3 to infinity. And what we want is a test point in each interval. We're going to test it into the second derivative. So I'm going to test x equals negative 2, negative 1, 1, and 2. And I'm going to plug those numbers into the second derivative and see if I get a positive or a negative. And here's the second derivative. The factored form is easier to plug into. So let's take negative 2. 20 times negative 2 is negative. Negative 2 squared is 4, and 3 minus 4 is negative. So we have negative times negative, which is positive. Let's take negative 1. 20 times negative 1 is negative. Negative 1 squared is 1. 3 minus 1 is positive. Negative times positive is negative. Let's take x equals 1. 20 times 1 is positive. 3 minus 1 squared is positive. Positive times positive is positive. And let's take x equals 2. 20 times 2 is positive. 3 minus 2 squared is negative. Positive times negative is negative. So what does that tell us about f? That tells us that f is concave up, and then concave down, and then concave up, and then concave down. So we do have inflection points. And they are at x equals 0 and plus or minus square root 3. All three of the pips turned out to be inflection points. If you want their y coordinates, then you have to put it into the original function. And then for the concavity, we can say concave up on the intervals from negative infinity to negative square root 3, union 0 to square root 3, and concave down from negative square root 3 to 0, and square root 3 to infinity. Next one. Number 7, same directions, new function. Let's find the first derivative, and that would be 1 minus 2 cosine theta. And let's find the second derivative, and that would be 2 sine of theta. Now let's see where the second derivative equals 0. And we can divide both sides by 2. And we're just on the interval from 0 to 2 pi. So between 0 and 2 pi, where is the sine value equal to 0? You can use your unit circle to help you figure that out. At 0 radians it is, at 180 radians it is. So that gives us 0 and 180, or pi, I should say. Not 180 radians, but pi radians. So we're going to divide our number line at those places. So from 0 to pi, and from pi to 2 pi. Let's pick a number to test in each interval. So I'm going to test pi over 2. And 3 pi over 2. I'm testing it into the second derivative to see if I get a positive or a negative. And the second derivative was right here. So what is the sine of pi over 2? Sine of pi over 2 is 1. 2 times 1 is positive. What is the sine of 3 pi over 2? Sine of 3 pi over 2 is negative 1. Multiply that by 2 and it's negative. So what does that tell us about f? That tells us that f is concave up and then f is concave down. And that tells us that we do have a point of inflection at theta equals pi. I wouldn't count 0 because that was the starting point of our interval. And then we'll just give our intervals of concavity. Concave up from 0 to pi. Concave down from pi to 2 pi. Okay. Number, my slides have stuck.